Okay, good afternoon everyone. Let's get started with a new chapter about transformer and large language model. So this is the most exciting chapter of this course, a lot of modern stuff. So large language model, ChatGPT came later of 2022, which bring a lot of excitement to the community. So here we prompted ChatGPT to make a syllabus for our course, TinyML and efficient deep learning computing, and this is the syllabus that comes out with a course overview, with the course objectives, prerequisites, and even come up with a pretty good syllabus: introduction to TinyML, edge computing, efficient neural architectures, model compression techniques, quantizations, prunings, and edge AI hardware. Makes a lot of sense. But serving and training such large language model is pretty expensive, taking a lot of GPU hours to train and run inference, to scale them up, both training and inference, very costly. So today we are going to first introduce the techniques behind the large language model. What is their workload? What does the workload look like? It's actually much more complicated than just matrix multiplication, lots of details. We want to understand deeply about those algorithms before we can accelerate them in the next lecture. So here are some other examples, like Google Translate can easily translate between different languages. And also here it shows the GitHub Copilot to write a piece of code to parse a list of expenses, and then it's going to automatically come up with the code generated by GitHub Copilot. And even multi-model large language model, building personal assistants, reading your screen, reading your pictures, understanding videos, like in this example, answer the question in the following figure, provide intermediate steps, like how long is this edge given here, and then GPT-4V can calculate 4 square plus 8 square equals C square, and then can solve for the C. And here, even there is a demo of using ChatGPT for practical use cases, trying to lower the seat. And it's asking how to lower my bike seat, and input it, take a photo and input it. To lower your back seat, locate the quick release lever. If it is a quick release lever, if not, you need an Allen wrench. And then I'm going to take a deeper, closer look, take another photo. And ask the GPT-4V, is this the lever, just to confirm some of the details. And it's going to say it's not a lever, it's a bolt. You need an Allen driver. And I'm going to input the menu and also a toolbox for this kind of interactive chat. And we are going to see those challenges dealing with those long context for such interactive conversation. Here is my menu and toolbox. Do I have the right tool? Yes, you have the right tool. Okay, in the left section of the toolbox, you have to do this, use this to loosen that. It can actually refer to reason across these two images. One is the menu, the other is the toolbox. It can tell you according to the menu, you should use this tool. Okay, pretty exciting. So we are going to witness some of the technical challenges, computing efficiency challenges for such interactive conversation, especially a long conversation. We're going to learn about KV cache, where as the conversation gets long, the KV cache will grow linearly, and how large that will grow and how prohibitive it's going to be, especially when we are trying to process videos, which contain many frames of images, and each image might be worth like hundreds of tokens, and your KV cache will soon grow pretty large. It will require lots of memory, become super expensive. And we are going to discuss techniques to make them more efficient. Okay, so this is the lecture plan for today. We'll first introduce the transformer basics. You may have heard the paper, transformer is all you need. Even the Nobel Prize is closely related to that, so we're going to learn what are the components of the transformers. And also we are going to talk about transformer variants, different changes, optimizations, and also introduce the large language models like Llama 2, Llama 3, etc. And also advanced topics, including briefly talk about multimodal language model. Okay, first chapter, transformer basics. So let's first revisit very quickly the NLP tasks. What are the categories of NLP tasks? What is the history? How people used to deal with it before the transformer era? Okay. Roughly two categories of tasks. One is discriminative task. The other is generative task. So discriminative task, given a sentence, we want to find some classification result, such as sentiment analysis, text classification, textual entailment, those kind of summary tasks given a fixed sentence. That is a discriminative task. The generative task, given the sentence, we want to generate the next token. So that's the language modeling. Similarly, machine translation, given an input language, translate to another language, and also summarization. So you need to generate new tokens, okay, new sentences. So those are generative tasks. And pre-transformer era, people have been using recurrent neural nets very widely for these tasks. Okay, so you have a fixed working memory, but it struggles to maintain those long-term dependencies. Okay, so if you have a pretty long sentence, you probably want to save a lot of information rather than compressing all the information within very small, very limited amount of hidden layer, as we did in recurrent neural nets. But it's pretty memory efficient, right? You have a fixed amount of, you have a fixed hidden layer. Okay, so unlike large language model where the KV cache will grow linearly, this has fixed constant memory, and you can also enroll it, okay, to different time steps. During the training time, you do back propagation through time to calculate the gradient. So there's natural dependency across different tokens. For example, the third token depends on the second and the first token, and that limits the training efficiency, since it has limited parallelism. You cannot compute this node before the node before it. Okay, the dependency hurts the parallelism. People have also been using convolution neural nets to deal with language tasks. Okay, so we can do 1D convolution, one-dimension convolution, and so these three tokens, 3 dimensions will impact x1 slash, x2 slash will depend on 0, x1, x2, etc. with a receptive field of 3. So we can have a sliding window, have a sentence. This movie has amazing, diverse characters, and we use a sliding window of 3. So each word has the embedding is hidden dimension is 3. We have a window length of 3, so that we can convolve with a 1D convolution and produce a result for the next layer, get a feature vector. So what is the limitation here for convolution? Very limited context information, right? You can only see adjacent 3 tokens. Unlike transformer, you want to see the entire sentence, okay, everything before it versus only adjacent 3 tokens. So naturally, we can deal with that by what? By stacking multiple layers, right? You can have 1 layer, receptive field of 3, 2 layers, receptive field of 5, and then on and so on. You can have a larger receptive field by stacking multiple layers. But within a single layer, the receptive field is very limited. So there are, for RNN and LSTMs, there are also 2 categories. One is bidirectional, one is unidirectional. Okay, so for the bidirectional LSTM, each token here can see both the previous state and also the future state. That's how we call it bidirectional. Versus single directional, each time step we can only see the previous time step. Okay, so bidirectional RNNs are used for discriminative tasks for encoding, versus the unidirectional RNNs are used for generative tasks like decoding. Because when you are generating a token, generating a new word, it is only dependent on the previous tokens. Therefore, unidirectional RNNs are used for generative tasks. So what are the problems with RNNs and our CMs? So first of all, it's hard to model those long-term relationships. Okay, so it takes a pretty long time for the information to propagate. It's actually all sequence-long steps to model the interaction between two tokens. For example, we want to model was versus chef. Okay, you have to go through many steps, all sequence-long steps, to model the interaction between two tokens. So images is fine. Images has locality. Okay? Two pixels very far away from each other may not interact. But languages doesn't have the locality. It's highly possible something you said much earlier is very highly correlated with some words, some tokens you just said a moment ago. Okay? So you don't want to go through all sequence enough number of layers to model the interaction between two tokens. And also it has limited training parallelism because of the dependency. Okay, so this is the computation graph for RNNs. This is step 0. You may have learned those in the prerequisite 6036. Step time 1, time 2, time 3, and this is the wavefront. You have to propagate the information. It has a dependency. You can now calculate all the embeddings in parallel. So that results in very limited training parallelism since the states have very strong dependency to the earlier states. Okay? And it takes n steps to get to step n. Okay? From step 1 to step n, it takes n steps. You cannot parallelize them, making the GPU training more difficult. So given those constraints, Transformer solves a lot of those problems. Okay? So this is the architecture of a Transformer block. We'll go through each component step by step, starting with the tokenizer, okay, and then how to embed the tokens, basically the embedding. And then we will talk about the attention mechanism, including the MHA, multi-head attention, to model the information between different tokens, and also the FFN layer to model information independently for each dimension, the layer norm, the residual connection, the positional encoding, and finally making the final prediction with a linear head. So let's start with the tokenizer, how to tokenize the words. So what is a token? Intuitively, a token is very similar to a word, but it's a basic component of a word. For example, large generative models, large itself is a word, it's also a token. And generative, that's a single word, but it has two tokens. One is generative, the other is relative. Okay, generative, so that's two tokens. And models, for example, actually they are divided into 4 tokens, E, dot, G dot. For example, in this whole paragraph, there are 110 words, and that translates to 162 tokens, which is slightly more than the number of words, because some of the words actually contain 2 tokens, like this one. Parallelism, so parallel is 1 token, ism is 1 token. Okay? And this hands-on experience, actually hands-on is 3 tokens, hands dash on. Okay, so that's the slight difference between the number of words and the number of tokens. Intuitively, you can just think about a token as a word. So we want to digitalize everything, right? So that we can process them by computers. How do we digitalize the words, the tokens? Okay, so that is the embedding. Okay, so we want to have a number to represent each token. One method is to do the one-hot encoding. So we have 100K columns. Say we have 100K words in the vocabulary, and and we have only one in each vector. Okay? So we have the first entry to be 1. All the remaining entries are 0. Good. Maybe the third one, just an example, third one is 1, the others are all 0. Moving, this one is 1. So it's one hop, only one of the entry is 1. And we need a lot of columns, since we may need to have a pretty large vocabulary. Each column in the vector represents one possible word in the vocabulary. Is this representation efficient? Actually, it's not, because the vector can get very long for a large vocabulary. And lots of them are 0. Actually, all of them are 0 except for only one value. Okay? It's a super sparse representation. You ended up storing a lot of zeros. A more efficient way is to represent each word using the word embedding, okay? Using a vector, a unique vector to represent each word. For example, here we are using three-dimensional hidden dimension to represent each word. The is represented by this vector 0.2, 0.4, minus 0.1. Good is represented by this three-dimensional vector 0.7, minus 0.5, 0.3. Okay? So such word embedding can be trained end-to-end for a particular task, for a downstream task. Some of the early pioneers in this area include the word-to-vec, the glove, word embedding. Okay? Nowadays, we can train them end-to-end given the downstream task. So in summary, each word is represented by a vector, okay? And that's called the word embedding, so that we can feed the sentences, digitalize the sentences, so that we can feed it into matrix multiplications. Okay, so after getting the embedding, we'll process each words, each tokens, and try to find the relationship between each words, each tokens. Remember, during the convolution and also during the RNNs, the limitation is the limited receptive field and limited parallelism. So let's see, how does multi-head attention solve those problems? So here we want to model the relationship between different tokens. Okay? Convolution only model the relationship between the token and its adjacent neighbors, like 3 adjacent neighbors, very limited receptive field. But now we want to attend to all the tokens, okay, all the tokens, so that they can interact with each other. So what do we do here? We have n tokens. We want to have n square matrix to model the interaction between each of them. So let's see how do we do that. On the right hand side is the computation flow. We first have a input vector, n tokens, each token, the hidden dimension has the hidden dimension. We divide it into 3 parts by passing through three matrices, query, key, and value. And then we query times the P transpose. We get the attention, which is n by n matrix. The n by n matrix indicates the relationship between each token. Since we have n tokens and n tokens, we get a square matrix. Optionally, we apply the mask, maybe the causal mask, softmax, make sure it sums up to 1, and then we multiply this weighted attention map with the V, the value, to get the output. In that way, we mingle the information between all the tokens. What is the intuition behind that? It is the query key value design is very analogous to a retrieval system. Just take a YouTube search as an example. So the query is basically like the text prompt in the search bar, which you are trying to search. The key is basically the title and the descriptions of any content, say video in this case. And the value is the corresponding video. And you first find the relationship between the query and the key. Okay, that becomes the a weighted map, a weighted attention map, and use that to do a weighted sum of the values. If some of them is very related, you have a larger weight. If it is not, if it is less, you have a smaller weight. Okay? So you have the information to model the entire sequence, not just adjacent 3 by 3, 5 by 5 adjacent tokens, but actually all the tokens. So we do the attention map by multiplying the QK transpose to get the inner product. We need to normalize by the hidden dimension, since different models may have different hidden dimension. Like Llama 2 has 4K hidden dimension. For 7 billion parameter model, a 70 billion parameter model may have a larger dimension. So we want to normalize that. And then we follow by the softmax to make sure each row sum up to 1. But what is expensive here? So the attention computation has O(n) squared complexity, since we want to attend each token with each other. Okay, have O(n) squared complexity, which is the bad part. And finally, we multiply the attention weights to do the weighted sum for the value, to get the final output. And let's see, what does the attention map look like? So this is attention map, an example of an attention matrix for machine translation. This English here, this is the French, like here. Most of the words are attending to exactly the same words, but some of them they are having the reverse order. These words actually correspond to the later word in English actually correspond to a later word in French. That's why we see this reverse diagonal. And the remaining words are in the diagonal direction, meaning that each token in one language corresponds to the exact location in another language. So the attention mechanism basically finds the correspondence between the words, and they are found by training, not by any rules. So that is just one head modeling one possible relationship. What if we want to model diverse relationships, okay, many relationships? So we want to add more heads to introduce this multi-head attention. So each head captures different semantics. So here we have multiple heads. First one, second one, third one, 3 heads in this case. They each has their own transformation matrix for the QKV. The final output is concatenated. We just concatenate the result from different heads and go through a linear projection layer, to merge those features. Why we need multiple heads? This is the visualization of different heads. Actually, we can see each head capture very different semantics. Some of them is just diagonal. Some of them it has some vertical information captured. So different heads are capturing the different subtle relationship between different tokens, adding the capacity to the model. And next, attention masking. Okay, so there are 2 kinds of masks. One is causal, the other is global. Okay, so this is a global attention map, meaning that every token can see every token. Even we can see the future token. Okay, so this is a global. N by N, everything is 1, that's the mask. Versus causal. Okay, each token can only see everything before it, but it can see nothing after that. Okay, we call it causal. So the attention mask basically is a triangle, is a down triangle. Since you cannot see the future tokens, each token can only see the past tokens. So the mask can be represented on the right-hand side. This is a global self-attention. This is causal self-attention. In global self-attention, each output can see all the inputs, no matter if it's before that or it's after that. But in a causal self-attention layer, each token can only see itself and everything before that. For example, token 6 can only see token 6 and everything before token 6 from 0 to 5. Okay, so that's the difference between the global and the causal self-attention. so the next part is the FFN layer. Since multi-head attention focuses on modeling the relationship between the tokens, but there is no element-wise nonlinearity. So we not only want to model the relationship between tokens, we also want to give some capacity to model the each token independently. So we added a feed-forward network, just a fully connected layer to help with such local feature modeling. The vanilla implementation consists of two matrix multiplications. One is projecting from 3D to 4D, pass it through a ReLU or G-LU, and then convert it down from 4D to D. Okay, so it can be represented by two matrix multiplications with ReLU in the middle. Okay, so that's the simplest implementation. And let's see, for a 7 billion parameter model, the hidden dimension is roughly 4K. For 175 billion parameter model, it's roughly 12K. And why do we have such inverted bottleneck? We want to add more information, okay, provide more capacity to the FFN layer. And later, we are going to visit some of the design variants compared with such simple FFN layer.
Is this the one that you're using to scale the query and the key vectors? Does it have like the normalization factor? These where what? You showed like 3 slides ago. You have like
The normalization
yes,
D square.
Is that
Yes, that D is basically this D. For example, 4K, this is the 4K, and where is that 4K coming from? It's actually exactly from here, the hidden dimension. Yeah. You can maybe just remember some simple case, like the 7B, the hidden dimension is 4K. And the number of heads is 32. Okay, number of heads is 32 in the 7B model. So 7B model is the one we are going to use in the homework, and actually it's quite widely used, easy to deploy. So, all right, and then we want to introduce the layer norm function. Previously, we have introduced the batch norm. So across the batch dimension, and also this is the sequence length dimension. Token 1, token 2, token 3, token 4. So this is sequence length dimension. This is the feature dimension, like 4K, hidden dimension D right here. So different from a batch dimension, we want to normalize across the feature dimension. And normalize across the feature dimension. Since different models may have different dimensions, we want to normalize them. Some of them may have pretty small hidden dimension like 700, some of them may be pretty big, 4K, 12K, etc. So we want to normalize across this feature dimension by subtracting the mean and also divided by the variance. Okay, and we have two scaling factor and a bias. Okay, this is a learnable affine transformation, the gamma and the beta. The gamma and beta actually turned out to be super useful. We are going to talk about that during the quantization part, like the smooth quant or using rotation. We can fold lots of the transformations into this gamma and beta. So when you're doing research, pay attention to this gamma and beta. It contains very few parameters, but they're super powerful. It acts as not only a function to stabilize the normalization, but also can fold a lot of computing, a lot of the smoothing, for example, quantization, lots of smoothing capabilities into these two factors. And there are roughly, historically, two ways to add the normalization. One is pre-norm, the other is post-norm. Post-norm basically says you want to first do the multi-head attention, then normalization. And then FFN, then normalization. And pre-norm is basically saying you want to first do the normalization, then multi-head attention. And layer norm, and then FFN. I'm having this bypass layer before the layer norm and after the MHA. Actually, the pre-norm is getting pretty popular these days due to not only better training stability, but also it's very easy to fold into the prelog of the matrix multiplication, making them into a single kernel. And also you can apply lots of the pre-processing. Say if multi-high detention is very difficult to quantize due to lots of outliers, you can fold it by smooth it by folding the factor, the multiplier into the layer norm. We are going to see more detail about that in the next lecture. Okay, so that's the layer norm and also the residual connection. So different from convolution, where position doesn't matter, since for region tasks it's space invariant, but in language the position matters. The position of each token matters. So we want to encode the position into the model. Let's see how do we do the positional encoding. Since attention and FFN, they do not differentiate the order of the input tokens. So let's see how do we do that. So positional encoding basically provides the positional information. The same token appears in place 1 versus place 10, they are different. So we want to add a unique encoding to each word's position in the sentence. Okay? It's a function of the location, the position. We call it absolute position encoding. So we have a raw word embedding previously, and we want to add to the raw embedding to add the positional information to the raw word embedding. So here we have an example. It's a 2D matrix. One is the feature dimension, like 4K. The other is the token dimension. Say you have here it has 50 words, 50 tokens, and here the hidden dimension is 128. In this case, this is the attention map. So what we add is that it's a function of the position. Okay, it's a function of the omega times t. Okay, and t here is the feature dimension. T is the token dimension. This is token dimension, and I is the feature dimension. And if you see the bars here versus here, they're actually quite different. That is due to the frequency is very different. Okay, as k gets larger, the omega gets pretty smaller. The frequency gets pretty small. So actually no change across different t dimensions. Versus here, the frequency is pretty high. Going from 0 to 50, the change is pretty significant due to you have a pretty high frequency versus here you have very low frequency. Okay, so this frequency is modulated. W is modulated by k. Okay? And k is related to I. I is basically the feature dimension. So here, for every I and every t, every token position, every hidden dimension position, you have a very unique combination of the position encoding. Okay, so here we can finally put it all together to have the entire big picture of the transformer architecture, including the tokenizer, convert word into tokens, and then convert tokens into embeddings. We can feed it with the multi-high attention for modeling the information across tokens, and the FFN layer to continue model the information within tokens, and then layer norm, residual connection, finally with the positional encoding. With the linear head on the top, we can make final predictions. And accuracy-wise, transformer surpass these previously published models in a fraction of the training cost. So here is accuracy measured by the blue score, okay, which measures the similarity of the machine translated text to a set of referenced translations, ground truth translations. transformer has higher Boole score, and this is the training cost, 2 or 3 orders of magnitude smaller training cost. Since the architecture, the design is quite efficient. Okay, now let's take a break before we jump into the design variants. All right, welcome back. So let's continue to discuss about transformer design variants. So most of the initial design have been very widely used in the community, but people designed several variants, alternatives. For example, the encoder-decoder model, encoder-only model versus the most popular decoder-only model. And also people design from this absolute positional encoding and improve it to relative positional encoding, only depend on relative position. Also several KV cache optimizations, for example, not only the multi-head attention, but a smaller version, which is the multi-query attention, and also group query attention, which is very similar to the normal convolution versus the depth-wise convolution versus group conv. A trade-off between the capacity versus computational complexity. And also from the FFN to GLU, the gated linear unit, which is quite widely used these days compared with the original FFN layer. So let's first talk about encoder, encoder only versus decoder only model. The original transformer is actually an encoder-decoder architecture. So for example, this translation task, we first encode the source sentence, translate English to German, this is good, and then we pass it through the encoder model, and then the decoder model is going to generate a token for the output. Okay, so an encoder on the left and a decoder on the right. Here we have more examples. Translation, acceptability, and also semantic similarity. Find the similarity between these two sentences, give a score, summarization given the input sentence, and summarizing to an output sentence. So we offer a unified text-to-text model for transfer learning on various NLP tasks. And the prompt is usually fed to the encoder. This is the encoding block, and then the decoder is going to generate the answers. Generate the first answer, and then the second token, and then the third token, one after another. The second category is the encoder only model, okay, like the BERT, which is bidirectional encoder representation for transformers. It is an encoder-only language model with 2 pre-training objectives. One is the mask language model, very widely used these days. The other is next sentence prediction, which is not quite widely used these days. So mask language model is saying we can mask away like 15% or a certain percentage of input tokens at random, and then train the model to predict those mask tokens. And those mask tokens can see both the token before it and also the token after that. For example, here we have created a mask. The movie is very boring. We put a mask and then here. We pass it through the encoder and then try to predict the mask work. Very rarely used task these days is the next sentence prediction to give 2 sentences and predict whether sentence B is the next sentence of sentence A. And then the pre-trained model can be fine-tuned to downstream tasks. So the attention mask for encoder-only model is like this, is full, because the token can see not only the future token, but also the previous token, but also the future token. So each token can attend to each other. Decoder-only model, the attention mask is only half, only the down triangle, since a token can only see the previous token. A token can only see the previous token, but not the future tokens. Okay? So GPT stands for Generative Pre-trained Transformer, is a decoder-only language model. And the pre-trained objective is the next word prediction. Okay? Given a sentence, we're going to predict the next word. So a robot must obey the order given it in trying to predict it. And that word can only attend to the tokens before that, therefore the attention mask is causal. Okay? It's only attending to something before it. And then similar to the previous, the pre-trained model can also be fine-tuned with different downstream tasks. And larger model, we don't even need to fine-tune, but can have this zero shot and few shot capability, which we are going to discuss them later. So just tell the task, or just give a few examples without having to fine-tune on a particular task. They can realize new tasks to achieve new tasks. Now let's switch gear to talk about absolute positional encoding versus the relative positional encoding. So absolute positional encoding fills the positional information into the input embeddings, okay, and also the QKV. So the information is going to propagate through the entire transformer, since the input embedding is the very source, the very beginning of a transformer. But relative encoding keep an eye on the relative distance information by impacting only the attention scores, okay, not the input embedding, but the attention scores, by adding a bias or modifying the parries of the keys, not the value, okay, since the attention map only depends on the parry and the key, it's QK transpose. And the advantage is that you can deal with long context. For example, reading a whole book, reading a whole movie, very long context. During training time, we may not have seen such long context, but we want to train short and inference test long. Okay? Train short, test long. So that's where that's the advantage of relative positional encoding. It's very easy to extrapolate for long context at inference time. So we'll introduce two kinds of relative positional encoding. One is the attention with linear biases, the alibi positional encoding. The other is the rotary positional embedding, which is the rope. So let's start with the alibi. The idea is to change the positional encoding to be only related to the relative distance. For example, Q1 and K1, the relative distance is 0. But Q2 and K1, the relative distance K minus Q is minus 1. And Q2, K2, the relative distance is 0. But here, Q4, K2, what is the relative distance? It's 2 minus 4, so it's minus 2. Okay? Similarly, here, Q5, K4, the relative distance is minus 1. So we have this extra attention map, which is the offset to the original attention map. Okay? So to add this offset to the original matrix, we define this as the relative distance. Okay? Instead of adding it to input token embedding, the input token embedding doesn't change, but only the attention map changes. And we can manually set this struct, which is multiplied with this position alibi position encoding and added to the original attention map, so that you can capture the information between the relative distance between two tokens. So although, for example, some of the token multiplied with each other is the same, but adding the relative positional encoding, the result might be different. The second one is slightly more difficult, but is very widely used. For example, Llama basically is using this rotary positional embedding. And so what we do here, we want to rotate the embedding in a 2D space. In order to rotate it, we first need to cast this very long, like 4K embedding into 2 dimensions. And how do we do that? We split the dimension from D to 2D over 2 pairs. Okay, so we have many pairs, we have 2 groups. The first half of D, the second half of D, we put them together, and now the entry of the first one becomes a 2D, becomes a 2-dimensional value, x1 and x2, and we can represent x1 and x2 in the 2D space. And then we are going to rotate it by m theta. Okay, m is basically the index. First entry, second entry, third entry, sixth entry. If the total hidden dimension is 12, the largest position is 6, since we are dividing them by half and put them into a 2D space. Okay, so m is the position of the token, and here this index is the position of in the hidden dimension. Okay, so we rotated it by m theta. Therefore, we added this positional information into the original representation of Q and K. So here we need a pretty big number to distinguish different tokens. So this is the theta representation is 10,000 to the power of minus 2i minus 1 divided by d. D is the hidden dimension. Okay, why do we need a pretty big number? Since each time when we rotate, we want to rotate a pretty small value. Otherwise, if you rotate by 2 pi, you come back to the, you cannot no longer distinguish these two vectors. Once you rotate by 2 pi, you come to the same original place. Therefore, we just want to rotate it by a little bit, Therefore, we have a pretty large value here in order to distinguish more tokens. And what if we use this approach, the rotation approach, and you just rotate the representation by grouping every 2 values into the 2D space and then rotate it? What if we multiply the query and the key using the rotated value? Okay, so this is rotating the Q and rotating the K. They are coming from different locations. One is m, the other is n, and here we are looking at the jth hidden dimension. We plug in. This is original Q, original K. We're rotated by m epsilon in this case, okay? And here rotated by n epsilon in this case, because m and n is their corresponding token number. Okay, corresponding token number. So this is a token number. Okay, don't misunderstand this m versus this index. So this index is related to the hidden dimension. Okay, this m is related to the token number. The first token, second token, third token. So this is within the first token, within the second token. What is the index of the embedding? You may have a 4K embedding divided by 2. It can range it from 0 to 2K. Okay. The phase angle of inner product of 2 complex numbers is basically the phase difference between these 2 complex vectors. So if you multiply them together, here we multiply the Q and K together. So the phase value would be the difference between the phase value of of Q and the phase value of K. Okay, so that's why here we have m minus n. So m minus n is basically the relative position. Okay, that's why we call it relative. That's why it's a relative positional encoding. It only depends on the difference between m and n, the token number between Q and K. Bit complicated here. I'll pause a little bit to answer questions. Yeah.
What is the intuition behind this? I understand you're rotating as a vector into the space, but how that incorporate the positional embedding into it by just divide it into 2 bits.
Mm-hmm. So you have say, like let's say you have 10 words, right? You have 10 words. the same word appearing in location 1 versus location 10, previously it cannot distinguish that. Now we want to distinguish whether this word appeared in position 1 or the last position, right? And that can be distinguished by the rotation. Okay? You rotate by m theta. M is basically your position, whether it's 0, 1, 2, or 10. If it is 10, that vector will be rotated by a larger angle. If it is 0, it will be rotated by a smaller angle. And the relationship between Q and K only depends on their relative location. It only depended on m minus n. Okay, and let's see what is the general form. Okay, previously we are just multiplying Q and K. That's very easy. Now we are doing the rotation by working on each pair of the value. Okay, so by each pair of the value, we are rotating them like m theta 1, m theta 2, m theta d over 2. Why d over 2? Since we are grouping the total hidden dimension, the d hidden dimensions into 2 groups. Each group has d over 2, and we put the first one and concatenate them together in the 2D space. That's why we have d over 2 right here. That's the general form of this rotation matrix, and we multiply this rotation matrix with the original matrix. That's a very simple implementation. So what is good about the rope position encoding? We can extend the context window. So we want to process very long context so that we can process very long documents, long books, long movies, for example. Like Llama, the original Llama, first version has 2K context length. Llama 2 becomes 4K, and GPT-4 used to be 8K. Okay, but it filled with larger context length. So we can actually extend the context length by the interpolation. Okay, the interpolation. For example, in the case here, previously we wrote it by m theta. If we are doubling the context length, we can rotate by m theta divided by 2. Okay, m theta divided by 2. So that's the intuition. Okay, we should interpolate. This is the original during the pre-training range. Okay? And we want to fit the same pre-training range. Previously from 0 to 2K. Now we want to interpolate from 0 to 4K, so that we put more doubling the frequency from here to here. Okay? We are interpolating a lot of dots in between them, so that we are falling into the same range, rather than falling into this unseen range during training. Okay? Rather than using this unseen range. So we want to change the theta to be theta divided by 2, so that we can fit a longer context. So here the blue part is the original context length. This green part is the interpolated context length. Okay, so that's positioning encoding, and now let's talk about the KV cache. Okay, introduce the multi-head attention, multi-query attention, and also the grouped query attention. So KV cache can be pretty large in long context case. Say, let's see this example. We have query key and value with 3 words here. I think of 3 tokens. I love trinium in this case. And this is embedding of x0, I, x1, love, x2, trinium. And we projected it into the q0, k0, and the v0. Q1, K1, V1, Q2, K2, V2. Okay, and then we calculate the attention score given this new word trinium. We calculate the attention score by multiplying QK with Q2 with K0. Okay, so this is query 2 with T0. This is query 2 with T1, and then we calculate Q2 with K2. Okay, So that's we use this as a weighted sum for the values. Okay, v0 times 0.3, v1 times 0.1, etc. So we need to store those keys and values for all the previous tokens so that we can perform the attention computation. So in the previous example, when we are calculating the second the H2, okay, we need to store the K and V for the 0th entry, for the first entry, etc. So that we can attend to them to calculate this attention score, like 0.3 and 0.1. So we need to put to store these keys and values for all the previous tokens in the somewhere. Originally, if we don't have a KV cache, we need to recompute each time. Okay, so here we have 4 tokens. Token 1 multiplied with the T1, K1, and we have to each time we have to compute everything from Q1, K1, Q2, K1, Q2, K2, Q3, K1, etc. With a KV cache, we don't need to recompute. Okay, given when a new token comes, now we only calculate everything related to that new token. And for all the previous tokens, we already keep it somewhere rather than recompute it. We only recompute for the new token. And then we store it in the KV cache. And finally, we can multiply with the value to get a weighted sum result. So we only need the current query token and only calculate the key and the value for the current token and store everything before that in the KV cache. And as a result, the KV cache will get longer and longer because as the sequence gets long, the KV cache will grow proportionally. So how do we calculate the size of the KV cache? We can calculate it in this way, like llama 2.7b. The KV cache will be, first of all, you multiply the mini batch size, and each layer you have independent KV cache. Even has you have an independent KV cache. And this is the hidden dimension of the KV cache, like 128 for each head. So 128 multiplied by 32 has, altogether we have 4K hidden dimension. This is the length of the sentence. We have multiplied by 2 because one is for key, one is for value. 2 bytes because FP16, that's 2 bytes. So actually that's half a megabyte or 12 kilobytes times the batch times the sentence length. Like for llama 2.13b, the layer increased from 32 to 40, number of heads also increased from 32 to 40, the embedding per head stays the same, 128 and 2 bytes. So 800 kilobytes times batch size times n. And similarly for the 70 billion parameter model, layer doubled to 80 layers. KV has also increased to 64, so altogether you have 2.5 megabyte per batch size and per token. Okay? And actually that can get pretty big. We plug in some numbers. If the batch size is one sentence, the length is 512, that's actually more than 1 gigabyte to store the KV cache. If the sequence length is 4K, which is roughly a paper, it will take 10 gigabyte just to store those KV cache. Not to mention if we have multiple users, like 16 users, try to read 16 books, 16 papers at the same time, it actually requires 160 gigabytes. Okay? Each A100 GPU, H100 GPU has 80 gigabyte of memory. So only storing the KV cache for 16 users, that will require 2 A100 GPUs. Each A100 GPU is pretty expensive, so that adds the inference cost. It can also actually exceed the model size. Okay? It grows much quicker. The model size actually stays the same. So this is how we calculate the model size. This is the KV cache size in blue for MHA. This is the batch size. As the number of users increase, the memory occupied by the KV cache will grow linearly, even surpass the model size in this case. So how do we deal with that? Can we save the KV cache by sharing some of the key and values? So that's the idea for multi-query attention. Compared with the multi-head attention, you have n heads for query and also n heads for key and value. Therefore, when we are calculating the size of the KV cache, we are multiplying with a very big value, the KV cache, KV heads. What we can do here is simplify n heads into just one head. For query, we still have n heads, but for key and value, we just store one copy. Okay? We just store one copy of the key, one copy of the value, compared with the multi-head attention. So this is the multi-query attention. Query stays the same, you still have a lot of queries, but keys and values are shared. You have just one copy of the key and value. Unfortunately, this will lose a lot of model capacity. So a trade-off in the middle is the GQA. Right? So GQA stands for group query attention. You have many queries still, like before, but a group of them, like a group of 2 queries, share the same key and the same value. Okay? So group of 2 queries share the same key and the same value. And as a result, altogether you have 8 query has 2 of them share a key and a value, so you have only 4 keys and 4 values. And typically, the ratio between group versus the total number of query has is 8 times. Every 8 elements will share the same key and value. This is pretty similar to the normal convolution versus depth-wise convolution versus group convolution. A trade-off between the model capacity versus the computation complexity. So let's see how does the GQA and group query attention and multi-query attention help. Which one will be the lowest? Multi-query attention. Right? Since multi-query attention, you have only one copy of the weights of the key and the value. So this is multi-query attention in the bottom. The number of heads is just 1. The group query attention, you have 8 heads, versus the full multi-head attention has 64. Okay? So that's the difference between these 3 different architectures with respect to the KV cache size. When the batch size gets longer, actually the reduction is pretty significant. And previously, you require 320 gigabytes for the 70 billion parameter model. Cannot fit a single node, but now it's below 80 gigabytes. It can fit a single H100 node. And let's see how is the accuracy impacted. Actually, the GQA can match the accuracy of the MHA under very large model sizes. Okay, so here is comparing MHA, MQA, and GQA for different benchmarks. You can see the multi-query attention sometimes lose accuracy a little bit, but GQA is doing pretty well, sometimes even higher accuracy. Therefore, in later networks, GQA is very widely used. The last change is actually from FFN layer into the gated linear units, the GLU layer. The difference is that FFN just consists of 2 simple matrix multiplications with such kind of inverted bottleneck with ReLU or GLU in the middle. But Sui GLU basically have 2 differences. One is there are 3 matrix multiplications, 1, 2, 3, and there is a gating element-wise function, okay, calculating the element-wise between these 2, the results between these 2 tensors, and then pass it through another matrix multiplication. And y here is 8d over 3. We have 3 of them, 8d over 3, 8d over 3, 8d over 3, and 3 of them is 8, same as 4 plus 4. Okay? And the second difference is here is using a different activation function, the switch activation function. Okay, switch activation function, first matrix multiplication, element-wise multiplication with another matrix multiplication, and finally do another matrix multiplication. And these two matrix multiplications can be fused into a single one. Okay. And complexity result-wise, you can see the using the Sui GLU is actually giving a pretty good result. And here is comparing different activation functions. So this is the switch function. This is the GLU activation function. They look very similar, I would say. But there's some subtle difference between between here and here. Okay. If you want to go deeper about the switch function. All right, so with that, we can introduce some of the modern large language models. So they are improving pretty fast, scaling up. People find scaling them up can have very good, many different capabilities. For example, we call it emergent ability. Okay? Scaling up the model will unlock more capabilities. Despite that, it's taking a lot of GPU memory. So this is the growth of the GPU memory, this is the model size. Why people need so much model size? Because they can have a lot of cool capabilities. For example, here we give it a very interesting task called modified arithmetic. The symbol represents a simple mathematical operation like 100 plus 200 equal to 301. Basically added 1 to the original answer. 1 plus 1 equals to 3. 2 plus 2 equals to 5. Okay, so this is a modified arithmetic, and this is the accuracy of this new task. When the model is small, the accuracy keeps very low, make no change, no improvement until a certain point. When the model gets larger, so this is measured in the model scale, measured by the trillion flops. Even through a lot of GPU compute, suddenly the accuracy gets much higher. Suddenly the emergent abilities will appear. Similarly for other tasks, like word unscramble, the capability suddenly increase when the model is larger than the 30 threshold. What is the word unscrambling? The word HTE is a scrambled version of the English word the. Okay? And similarly, the word SOHPTO to a scrambled version of English word photos. Okay, just reshuffled the order of the word and trying to decipher what is the original word. So that's the word unscramble, and the ability doesn't appear until the trillion flops exceed a certain threshold. That's why we need the large language models due to those emergent abilities. So GPT-3 basically scaled up on top of GPT-2 to be few shot learners, and they enabled in-context learning capability. So these are very important concepts. So what is few shot learner? What is in-context learning? So in order to learn a new task, previously we have to fine-tune the model. Okay, pre-train it and then fine-tune it on the specific task that is desired. For example, translation, we give an example 1, calculate the gradient, update the model, do another iteration, example 2, give it a ground truth between these two languages, do the gradient update, and finally we get a new model, feed it into a new prompt, and try to get a new answer. Okay, so that's learning through fine-tuning, which require backpropagation, pretty expensive. And people find that once we scale up a large language model to a much bigger value, bigger size, we can generalize to new tasks without having to fine-tune them. But through zero-shot learning or few-shot learning, zero-shot learning is basically saying, tell me the description of the new task, and then we can achieve the new task. Few-shot learning basically says, given a few demonstrations, given a few examples, without telling me what is the task, how to solve the task. It can help me solve the task. For example, this is zero-shot learning, predict the answer, only given a natural language description. Here, the description is translate English to French, and then given the English, it will predict the French. Okay, so this is no gradient update. We never trained on many English to French pairs. We never trained on that. And few-shot learning, in addition to the task description, we also want to give it a few examples. Right? Example, English-French pairs, and then given a new word of English, it's going to predict French. So that's few-shot learning. And these large models, okay, when the model gets larger, the few-shot learning capability begins to appear in this area. Okay, so there's 175 billion parameters. This is accuracy, this is the number of examples in the context. As you give it more examples in the context, the accuracy will increase for these big networks. But for these small networks, no matter how many examples you feed in the context, the accuracy doesn't quite improve. So this is the GPT family, actually growing pretty fast. Later ones are not released, so we don't know. And then the open source version quickly catch up since about 2022. The first one is OPT model, an open pre-trained transformer, large language models. Meta open source different sizes ranging from 125 million to 175 billion. This is zero-shot capability. This is the few-shot capability. And it has it's a pretty pioneering work. Enable us to do a lot of research. Here is using a very simple random activation in FFN. It's using pre-norm. It's a decoder-only architecture. And then Meta released this Llama model. Okay, and here it's using the switch LU, switch activation function, followed by the gated linear units. Gated linear units is basically three matrices, 8D times divided by 3, and it's using rotary positional embedding. We just talked about that. The rotating interpolation. The 7 billion parameter model has 32 heads, 32 layers. Context length is only 2K at that time. Hidden dimension is 4K, since the hidden dimension for each head is 128. It has 32 heads, and it has much better performance than the previous open source models. And later, they built a Llama 2, which extended the context length from 2K to 4K. So, and also the training token increased from about 1 trillion to 2 trillion tokens. And still, the performance has not saturated. If you keep training, the accuracy will, or the perplexity will keep decrease. Llama 2 introduces this GQA, the group query attention, to save the size of the hidden cache so that it can fit longer context. This is for the 7B model. Okay. It also introduced instruction-tuned version, okay, using the supervised fine-tuning to align with the human result. That's the Llama 2 chat. And here is comparing the capability between GPT-4, Llama 2 still behind. So this is where we were in the last year's lecture. And this year, very exciting, Llama 3 came, trained on even larger corpus by even spending even more GPU hours. Actually, more training tokens from 1.8 trillion tokens to 15 trillion tokens, or multilingual tokens. And the GPU resource consumption is much higher. It's 50 times more flops than Llama 2. Okay? The flagship model has 405 billion parameters. So if one GPU is 80 gigabytes, you can easily calculate how many GPUs do you need to serve the model. It has even larger context length. Base model has 8K. The instruction tuned version has 128K, the long context version. The post-training technique, we'll talk about these, supervised fine-tuning. rejection sampling, and DPO, the direct preference optimization techniques. And a very small model, a very popular small model is the Mistral 7B model. Okay? So it outperformed Llama 2, even 34 billion parameter model. An interesting part here is the sliding window attention rather than the full attention. Here is using the sliding window attention, and also using you can stack multiple such techniques to achieve a longer context length. Since just one layer you have limited context length, you cannot see everything before it. But after a couple of layers, receptive field is going to propagate and finally gets longer. But it's deprecated since V2. A very interesting part is the chinchilla law, which is describing the relationship between the parameters and also the number of training tokens. So basically it's saying that the parameter, as the parameter grow from 400 million, 1 billion, 1 trillion, the number of training tokens also need to grow. You cannot just grow the model without growing the data. The data and model has to grow up proportionally. However, the trade-off is different when we consider the inference computation. For example, Llama model is trained on much larger amount of tokens. Okay, from like 10 billion parameter model, the model is trained by a much larger amount of tokens than 200, way beyond 200 billion. It's actually 2 trillion tokens, so that we can spend more on training so that the inference cost will be lower. With the same number of parameters, the accuracy will be higher. All right, so with that, we'll conclude the lecture today. Later, we'll continue to talk about those advanced topics in the next Tuesday's lecture.